We've spent this lesson learning how data is collected and described. In this video, we're going to answer the question, how is that data actually used in nutrition and public health, and what meaningful things it tells us? We'll start with demographics, which are population characteristics like age, sex, race, ethnicity, income, location. These define who's being studied, and so it allows us to break data into meaningful subgroups. From demographic data, we calculate major epidemiologic indicators. The most important pair of this is incidence versus prevalence. Incidence measures new cases over a defined period of time divided by the total population. It tells us how quickly a condition is developing or spreading. Prevalence measures all existing cases divided by the population at a given time, so it tells us the total burden of disease. Incidence tracks the new development, while prevalence reflects the overall burden. Next, we have morbidity and mortality. Morbidity is the rate of disease, the number of people with a condition per population. And mortality is the rate of death, the number of deaths per population. Infant mortality rate, specifically, measures deaths under age 1 per 1,000 live births. These ratios standardize health data, allowing us to compare populations and identify trends. In addition to understanding disease burden, we also need to understand the systems that identify who may be at nutrition risk, and these are called nutrition screening tools. Nutrition screening tools are standardized, evidence-based methods that are used to quickly identify patients who may need further nutrition assessment. These tools help support early intervention and so improve outcomes. And they also help organizations meet their regulatory standards. We'll cover individual screening tools in greater depth later. But for now, we'll use sensitivity and specificity to evaluate whether a screening tool is effective. Sensitivity is the true positive rate, meaning it measures how well a tool identifies individuals who truly have the condition. A high sensitivity means there's fewer false values. So a test with high sensitivity is valuable when missing a diagnosis could delay treatment or worsen outcomes. Specificity is the true negative rate. So it measures how well a tool correctly excludes individuals who do not have the condition. High specificity means there's fewer false positives, which reduces unnecessary interventions, and it also reduces the extra burden of false diagnosis. So in practice, highly sensitive tools are prioritized when missing disease is dangerous. Highly specific tools are prioritized when overdiagnosis would create unnecessary burden. For the RD exam, you may need to interpret these metrics, you might need to compare screening tools, or you might need to determine which is most appropriate for a given clinical setting. But to fully interpret healthcare and nutrition research, we need statistical tools to help us analyze relationships, significance, and evidence quality. And so in the final part of this video, we'll look at two essential tools that help us evaluate research findings: the correlation coefficient, also known as the R value, and clinical significance, also known as the P value. These two are absolutely foundational. If you're going to remember anything about interpreting research, remember R value and P value. The R value tells us the relationship between two variables. Specifically, it answers the question, when one thing changes, does the other thing change with it? If fiber intake increases, does blood glucose go down? If calcium intake goes up, does bone density rise? This is called a correlation. But it's important to remember that correlation does not necessarily imply causation. Just because two variables move together does not mean that one causes the other. P-value, on the other hand, looks at probability. It asks, is the relationship we're seeing likely due to chance? And this is where we can start to think about causality, because a low p-value means that the results are unlikely random. The lower the p-value, the stronger the evidence against the null hypothesis, the idea that nothing is going on. And we'll look at both of these more closely. Again, that R value is the correlation coefficient, and it tells us how closely two variables follow a linear relationship. This number ranges from -1 to +1. An R value of +1 means perfect positive correlation. As one variable goes up, so does the other. Imagine plotting daily protein intake and muscle mass in athletes. As protein increases, muscle mass should also increase, producing a strong positive correlation. An R value of 0 means there is no correlation at all. One variable has no predictive effect on the other. You could be looking at coffee intake and shoe size, two variables that just don't relate. A negative R value means an inverse relationship. If one variable goes up, then the other goes down. Like as sodium intake rises, potassium intake decreases, and that could reflect a negative correlation. The strength of the correlation is based on how close the R value is to either +1 or -1. The closer we get to those extremes, the tighter the relationship appears. But don't forget, R values show patterns, not proof. They don't tell you if one variable caused the other to change. Now, let's focus on p-value, which is how we test for statistical significance. The p-value tells us the probability that the results we're seeing happened by chance. In most research, the cutoff that we care about is 0.05. If a p-value is less than or equal to 0.05, we say that the result is statistically significant. This means that there is a low probability that the observed difference or relationship is just a random fluke. So if we compare two diets and find a difference in weight loss with a p-value of 0.03, that suggests that the difference is probably real, not just chance. But if that p-value is 0.3 or greater than 0.05, we can't confidently say the diet has had any real effects. There's too much probability that randomness explains in the results. The lower the p-value, the more confidence we have. A p-value under 0.01 or 0.001 means the results are very unlikely to be due to chance. This is the key when evaluating nutrition studies. If a new supplement lowers cholesterol, but the p-value is 0.07, it might look promising, but statistically, it's not significant. The difference could easily be random. So p-values help us decide what's worth trusting. Let's bring this lesson home with the major type of statistical tests and when you would use them. These are the tools researchers use to analyze their data and reach conclusions. We already talked about the R value and the p-value. And if this is all your brain has space for, stop here. But you could get questions on the other statistical tests, so I at least want to briefly expose you to them. The correlation coefficient is R value. You use this when you're looking for a relationship between two continuous variables. But even if the R value is strong, +1 or -1, it does not prove causation, just correlation. You'll use the p-value anytime you want to know whether your result is due to chance. If your p-value is below 0.05, then the difference is statistically significant. If you're above 0.05, you don't know whether the intervention is having the effect or if it's just random. The chi-square test is for categorical variables. If you're analyzing yes or no outcomes, like whether someone has diabetes or not, or whether they're using a supplement, the chi-square test helps you identify if the distributions across groups are different. For example, is supplement use different among people with and without food insecurity? Chi-square would help answer that. Confidence intervals help understand how precise a study's estimate really is. Instead of saying the diet reduced BMI by 2 points, a confidence interval gives a range. Like the true BMI reduction is likely between 1.2 and 2.8 points. The smaller or narrower that range is, the more confident we are in the results. T-tests are your go-to when comparing two groups. I like to visualize a T-chart, like a pro-con list, to remember this. If the study is looking at average fiber intake between different groups of men and women, a T-test will allow the researchers to compare between the groups. And finally, ANOVA. This is like a t-test, but for 3 or more groups. Maybe you're looking at sodium intake in low, middle, and high income groups. ANOVA helps you see if at least one group differs significantly. All of these statistical tools help us move beyond assumptions and into evidence. They are the foundation of evidence-based practice. These tools will help you think critically about what the data says and what it doesn't. You now have a strong foundation to evaluate scientific studies with confidence, spot weak evidence, and use solid data to inform your practice. Great job sticking with it.